So I'm going to cover a few miscellaneous topics. Let's start by talking about the files in the root directory. When you boot, it loads kernel.bin, and kernel.bin runs atom cpp.z. Kernel.bin loads compiler.bin and then starts executing. This is like autoexec.bat, or this is the startup script. So in the root directory, atom is the startup script, and the entire atom directory gets processed in inside of the startup script, changes to the atom directory, and then it includes a bunch of subdirectories. And then this is the startup task is called Adam, like Adam and Eve, and so the first task is Adam, and all this code that he includes gets put in his symbol table. You can think of the scope like an environment variable. So Adam is the father of all tasks, and if you say who, this shows all the symbols. Well, you have to doc max. This makes an infinite command buffer, and then who. So this is all the these are all the symbols. Most of these are in Adam's table. If you want to see local symbols, you can say who -r. There's do it once. So that's a that was called during boot. If I say I64I and then I say who again, now we have two symbols. So there's only a couple local symbols. The rest, you inherit the symbols of your parent. And on CPU 0, there's the Adam task, and then he has children. Now guess where those children come from? Remember, at startup, it's just Adam including the script. So if you're paying attention, if you're paying attention, inside of Adam, at the bottom it goes into your home directory and includes files. And when your home directory starts empty when you do a fresh install, and if you okay, so what happens here is it's including files in your home directory, and if they're not found, it searches the parent directory. So this is just like the symbols. The way the directory tree works is just like the symbols. If a file's not found, it searches the parents. So basically, what this enables is this lets you override with your own files in your home directory. So if you look at my home directory, I have Adam sys. This gives my own custom. This is where right here are where the two terminal. When I reboot, I'm going to reboot. Watch this. When I reboot, I have two terminal windows. That's what everyone has. Oh. Anyway, when this file gets included by Adam, and it generates two terminal windows. These are terminal windows. And it also starts up my autocomplete initialization, so that scans for words and symbols. So you can customize startup. Technically, all the oops, dang it. All the files, all these Adam files are just. I broke it in pieces so that you can include the standard. So this is for if you want to customize your keys. You can make your own key customization. Localization. This is for the time zone. This will speed up the keyboard, and this sets the mouse speed. Packages. So technically, you can trim so that you don't include as many tools. Some of the Atom files are optional. The only reason we have these broken down is so that if you upgrade, it might work without changes. But I don't make any promises on upgrades. Upgrades, it'll probably break your files. Anyway, so the Atom. So let's do something. I'm going to put on echo. There's no echo symbol defined. Anyway, now I reboot. This is a reboot. All this code is all those files that are getting included. It starts with some headers for the kernel and compiler, and then the rest of it is just-in-time code that gets put in Atom's symbol table, and the code is in his memory space. Kernel memory and other operating systems, the Atom heap is like kernel memory because Atom never dies. So if you tell Atom to allocate some memory, that can be used system-wide. Actually, all memory there's only one address map, so all memory can be used by all tasks at all times. But Atom memory never gets freed. So, for example, let's just say you wanted to include the wallpaper demo. There's a wallpaper demo. Now, guess what you have to do? If we ran this as user task, then when the task died, the code would disappear, and then it would crash because the code would get freed. But if we tell it to Atom include, you only do this a couple times. I never do this, to be quite honest, but it's here if you need it. If you Atom include, now the code is in Atom's heap, and so the graphics are so expensive, you probably don't want a wallpaper. Anyway, what I mean is, I'm afraid, oh, I didn't mean to do that. Anyway, my graphics are slow, so you wouldn't want to do big things on your wallpaper. So, like I said, there's only two binary files, kernel.bin and compiler.bin, and the rest of it is just in time. So that works out to about half and half of half the code. It's about 80,000 lines. About 40,000 is kernel and compiler, and then the other 40,000 is the graphics library and the document framework editor and the tools. I go ahead and put grep and stuff like that. Grep, all that code is loaded into Atom's. Atom compiles it. So it's on a normal operating system. You do it when it's. I did make some utilities that you use conventionally. There's on my website. There's a link to these files, and you can play with them. This one tells me if I have any lines greater than 80 columns. So this is like a normal utility you include. But as a matter of fact, most of the utilities are are loaded in memory. So there's a FindFile. When you start writing code, you're going to use the FindFiles. This is like find first, find next. There's some flags. You can tell it to limit it to. Well, FF is this is the simplest. The FF is will display a list. Other utilities require a list of files, and if you want to practice and see what is included, like if I say /Atom /B star, how about that? So this just tells you what a mask will pull up. You can use FF if you want to see what a mask will pull up. Now if we say just about I want to do the autocomplete directory. The autocomplete directory has some binary files. Now there's some flags. If you say +T, it'll only do text files. Now we don't have those binary files. You see the binary files down there? So now if you do, you can limit it to source and stuff like that. Source code. Anyway, so there's one in here for what you can do is on a normal operating system you use find first, find next. Well, this pulls up all the files in a tree all at once. Now I'm sorry. This FindFiles is what whenever you want to process files, you use FindFiles to. This is like find first, find next, except it pulls up all files at once. And there's some flags. We can FOF. What is it? FF. Find. It's in the. This is so handy that there's even a help entry for it. File utils. Okay, so somebody asked about ordering. When you have a hard disk, it has a disk head or multiple heads, and if you order your operations in a smooth direction, the head doesn't have to jump around. So when you pull up a list of files, you can tell it to sort by the. First of all, you can tell it to flatten the files so that you don't, so that it doesn't return a tree. It just returns a list. If you say just F gets rid of the directories. Flatten, or no, that's files. Anyway, these are the flags. Sometimes they're text, sometimes they're binary. The way you tell is, oh, by the way, there's the file masks. For source code, you have, there's the masks. So there's a shorthand. You can say +T for text, +O to order them, sort them. Anyway, so like right here in this utility, we have FU file utility flags, and notice it's a string pointer. So this means we do text. However, this subroutine has a binary FUF flags. If it has an FUF, then that means it's binary. So in order to use the FUF, you have to give it, unless you can say FUF just files or FUF. Anyway, so pay attention to whether it's whether it's an integer or whether it's an integer mask or whether it's a string. This will convert strings to the integers. This is FUF flags. So these are the bits for the flags. So pretty much, you know, in Unix each utility has its own set of flags. In TempleOS there aren't that many utilities, so all utilities use the same flags basically. So if you go to command line routines, all these utilities use that FindFiles, and they all use the same. So diff uses FUF flags. I think it does. It should. Diff will compare. Okay. Oh, it has diff flags. Okay, diff flags are. this is for one file. This is not for multiple files. If we go to the bottom, that's for zipping. There's a merge. I guess we have to do merge. Okay. There's a merge utility that calls diff. Merge calls diff. And diff will let you merge. This is, I don't have, I can't use git. I can't use git, so let me make a change to this file. I keep my a standard install has all your file identical image on the C and D drive. So what I do is I do every time I'm working on code, and I want it. This is how I do commits, kind of. So I'm going to do a merge check between C and D. Now it just pulled up a duplicate. I made that duplicate. I'm going to tell it to use my backup. So that's my rant. Remainder all file 1. Okay, so that's how I what I do anyway. So so there's not an include directory. There's not an include directory. All tasks inherit symbols of parents, and all the code headers and in the Atom startup file, it starts with kernel headers and compiler headers. So there's two binaries. At this point at this point we've compiled 47,000 lines of code. So that's the Atom directory. And when I'm going to do a make all. Now we're up to 95. So we just doubled it. I just compiled kernel.bin and compiler.bin. So half of it is ahead of time, half of it is just in time. And so there's no include directory. Anyway, so when you run a game, for example, or if we do Hello World, so let's just do Hello World. I'm going to go to my home directory and say edit hello.cpp.z. Now I say hello world. Now I hit escape. That saves it. Then I say directory. Now I say pound include. There it is, hello. Pound include hello. I think I can just say that. Okay, so now as a matter of fact, this is I'm going to make it into a function. So you don't have a main in your files. I'm going to tell it to include it again. Now I did it 3 times. Now if I say who -r, so we have some other stuff in here. Remember, I ran the make all. It left some garbage. So my hello has been compiled. My hello is in memory. So if I say unassemble address my hello, so it's a call to print, and it has a string. Here's the string. Here's the string down here. Hello world. It doesn't have sections for data and for code. Everything is read, write, execute available at all times. Just imagine it's a Commodore 64. So the compiler just in time compiles. It compiles. It's not a virtual machine. It's not an interpreter. It's a goddamn compiler, and it compiles to 64-bit code. And So there's the code. It calls print, and there's the text. So now somebody was asking about. I used to have separate accounts for. There's only one account. The home directory is one. It used to have sub accounts, but there's only one account because I want it simple, and that doesn't help very much. Anyway, so there's no login when you boot. There's no login. There's no password. Remember, I said memory is 100% accessible. So, for example, let's say, what do I want to do? Did I reboot? I'm spacing out. Okay, so let's say we take the address of my hello. Now we can come over to this task. I'm having some difficulties. Okay, so my hello, we can unassemble that. On a normal operating system, you cannot access another task's memory. On this operating system, everything is available for all tasks at all times. So we can say 3F. Now we're not going to have symbolic debugging because the symbol table. Notice how when I unassemble it here, we don't know about the symbol my hello, so that it's not representing this as an offset, and it's anyway. So since all memory can be accessed, like if he makes a variable I equals 1, 2, 3, 4, address I. Let's just say I64 star pointer equals 0x 3f c7 4328. If I say star pointer, okay, so we can access his memory. By the way, if you tell Adam to make a label, if you say I64, let's say G, if you tell Adam, that's how you tell Adam to do stuff. The Adam task is the Adam task has a window up at the top, and I just told him to make a global variable. Now if I say G2345, now suddenly this task, since it's a global variable and it's Adam's variable, that G variable is system wide because it's an Adam's table. So if I say G2345, anyway, so you can tell the Adam task to execute code. I never do, but I don't know why I'm wasting your time. This is kind of neat. If you tell Adam to say hello, you can't type commands to Adam, but we can tell him to say hello. It's kind of tricky. Okay, he said hello. You see, he said hello. So he stays in a server loop. I tried to document that. I don't know what just happened. Anyway, I tried to document if you say F1 down at the bottom, task. So here's the Atom. Atom is on the core 0 is known as the bootstrap core, and other cores are known as AP cores, auxiliary cores, and core 0. So core 0 has the Atom task. The other cores have a server called the Seth task. Seth in the Bible is the son of Adam. So Atom stays in a loop, processing commands. Seth stays in a loop too, doing commands. Anyway, so I wanted to say that I have banned encryption and I have banned passwords because all memory can be accessed, and so nothing is safe from another task. So instead of giving a false sense of security, obviously I can't enforce it, but I've banned passwords because there's no security. So one task could monitor another task. As a matter of fact, I've put work into puppeting tasks and stuff. Anyway, so the memory can be freely read. So as you're typing the password, another task could spy on it. Now, there's if you hit F1 under the disk routines, the conventional C, FOpen, FClose, we have read blocks. Now, honestly, you're not supposed to use FOpen. What you're supposed to do is use the document framework and process text files. There is an FOpen, and it has some flags. You can say read, write plus, contiguous. My vision is we're going to tell Microsoft and Linux to support Red C, and the only all files will be contiguous. And what I'm going to do, so don't. That means you cannot grow the files because they're contiguous. So I don't recommend using contiguous files. So you might ask, well, the standard way you process. There is a demo of raw block access called there's a database. So this does raw blocks for a database. You can look at that for there's a good example, sort files. Well, anyway, where is a good example? DALDocs, that's where it is. No, I don't know. So what you're supposed to use is the DALDocs routines for text. If you're processing text files, use DALDocs, and read the whole file at once and write the whole file at once. So doc read, doc write. If you want it, you can put it in memory into a memory buffer or load it from a memory buffer. Anyway, read and write. Well, I could do an example. No, I don't feel like it. Anyway, let's go to there. Here's an example. So I made a utility. To check if I have. If you go to my website, under my website looks like this. You see where it says TAD files? Click on that, and then you can. These are some files that are not on the distribution, and one of them is for long lines. So I use this to give me a warning if I have any long lines. So I just went through I have a mask, so it does a recursion. This plus R is a recursion. It flattens, and it's just source code. I limit it to source code, and so I pull up a linked list of files, and then on each one I give it the name and the number of columns. So we want to limit to 80 columns. Let's just show you what happens if we say, okay, so if I say long lines star, let's say 79 columns. Column 79. Oh, I did long lines. Okay, long lines. I'm surprised we don't have a lot more. I think if I said slash, so this is, yeah, okay. Those are all examples of files with 79 or 80 columns. Anyway, so this is a pretty generic. Now notice up here I did when I was processing the individual file, I did doc read. That loads the whole text file. Now these files can have graphics, and that's a good reason why you want to use the doc read, and don't do FOpen. There is no fprintf. There is no fscanf. There's only raw blocks, and there's these whole files. So you're going to have to get used to the way the document is structured in memory. So there are different document commands. They're in a circular doubly linked queue. So if you go to docs, so there's different commands: text, carriage return, soft carriage return. That's for word wrap. So there's all these commands. They're in a circular queue, and when you're making a utility, then you process. Notice right here I say if it's a new line. Okay, I didn't check for text. Normally you say if it's text. Anyway, okay. There's an XY on each of the nodes in the queue, and so I got fancy and I checked for a new line past a certain number of columns. So at the end of each line is a new line, and I checked the X coordinate of the new line. So I got tricky. So that would work even if it was not text, but a link or a tree or something. Anyway, so that's what I wanted to talk about.